Hello and welcome to another video on basic fiber optics. Today we're going to explore the connection between signal to noise ratio, symbol error rate and bit error rate. So in the previous video, which will be linked right up here, we explored how to determine the signal to noise ratio based on a measurement of an optical spectrum by computing both the noise power and the signal power and then taking the ratio. So we saw that if we have a high signal to noise ratio, for example if we put in a filter that removes a lot of the noise power, we were able to get a very sort of clean, nice pulse being detected, where it's very easy to distinguish a 0 from a 1. But if you have a very broad filter, or maybe even no filter at all, the increase in noise is going to make the pulse a bit more fuzzy or scrambled. And I mentioned in that video, the previous one, that if the pulse has more noise, there's a greater risk that we'll misinterpret a 0 as a 1, or maybe the other way around. But I didn't explain exactly what is the mathematical connection between the signal to noise ratio and the exact probability of making that kind of misinterpretation. That's what we're going to check out today. Now, before we go into the details, let's first think about how we can even send data from one location to another one. So one typical way we can do that is by picking a modulation scheme. In this case, we're going to take a look at what's called 4-QAM. The idea is that if you have a data stream of zeros and ones we want to send from one point to another one, we first divide that bit stream up into a string of sub-bits, for example, 0, 0 and 0, 1, 1, 0 and 1, 1. And we refer to each one of these like little substrings as a symbol. So for example, 0, 0 would be one possible symbol, 0, 1 would be another symbol, and so on and so forth. Then we map every single one of those substrings to a certain voltage level. For example, we can map 0, 0 to a small voltage, 0, 1 to a slightly higher one, and so on and so forth. So we get 4 different levels here. That's where the 4 in 4-QAM comes from. Now the basic idea is that if we want to send data from one location to another one over here, we simply have a pulse laser that we send through a phase modulator. And so when a pulse arrives here, we apply a certain phase shift that corresponds to whatever bit we want to send, or rather bit string we want to send. So that gives the electric field a small phase shift. Then we send that pulse through a fiber, maybe even an amplifier, and onto a photodiode over here in the other end where we want to detect the signal. Then that photodiode is also being exposed to a reference laser. So the idea is that once the reference laser, or the electric field from that one, interferes with the electric field from the pulse, then we'll generate a beat signal. And because we've already phase shifted this electric field over here, the exact phase of that beat will then tell us what was the original bit string that's being sent over here. So right here we see a sort of crude example where if we have a very small phase shift, then we can interpret that as a 45-degree phase shift. That's like 0, 0. If it's slightly greater, then it'll be a 0, 1, and so on and so forth. So in a way, these exact phase shift values don't really matter so much, as long as both sender and receiver have sort of an agreement between what kind of phase shift corresponds to which symbol, then the data can be recovered over here from whatever was sent back here. Now, this is a very idealized situation where we're assuming that essentially in this diagram here, I'm sort of ignoring any kind of noise that's present, we're ignoring any sort of shaking back and forth here of the phase, which would change this phase method value. We're also ignoring any kind of amplitude fluctuation that might arise from the noise from the EDFA. But if we actually measure a lot of symbols coming in and then draw this kind of clever chart here in polar coordinates where we draw both the, let's say the electric field or corresponding electric field amplitude of the incident signal as well as the measured phase, then essentially we're going to get something a bit more like this, where instead of every single symbol being exactly at a certain location, a certain distance away, with a certain angle, it's sort of going to cluster around each one of these points right here. So that's because, of course, if we have a realistic situation, there's going to be a bit of noise. So we don't always measure, for example, 45 degrees, maybe we measure 44 or 43 or 46 once in a while, and we don't always measure the exact same amplitude. That's also going to fluctuate a little bit. But on average, because the noise coming from EDFAs is incoherent, we're going to get sort of a Gaussian probability distribution right here along each single one of these points. So you have to imagine sort of a 2D Gaussian probability density being centered at this location with a certain width. So as you can probably imagine, the signal to noise ratio is going to be basically the ratio between the amplitude of the incident field and this sort of the standard deviation of the Gaussian distribution we get here. Or to be specific, actually, the way we define signal to noise ratio is that it's going to be the square of the amplitude here divided by the variance of that distribution. But the general point is that for every single one of these points, we can create a essentially what you can think of as a 2D Gaussian probability distribution that's centered at this location right here. So here we have the sort of average field strength, and then we have the variance right here. And that gives us the probability of finding a symbol that was intended to be 0, 0 anywhere in this 2D plane. So for example, we can sort of think about the symbol error rate then as the risk of a symbol that was intended for this quadrant up here landing in any one of the other quadrants. So to find that error rate, we can simply take 1 minus the probability of landing in the first quadrant, because obviously the probability of landing outside the quadrant will be, the probability of landing anywhere in the whole plane minus the probability of landing where you intended to. That gives us the simple error rate. So this integral right here, it looks maybe a bit intimidating, but it's actually not too difficult to compute if you look up the definition of the so-called error function, which is the integral of the Gaussian. And in the end, you can show that the simple error rate is given by this formula right here, where the signal-to-noise ratio appears with a square root in here. Because remember that the signal-to-noise ratio is going to be the square of a over the variance. So in any case, so the simple error rate tells us what's the risk in probability, simply, of a given symbol being misinterpreted as something else. Now, this exact expression here only works for 4-quam. There's going to be a different expression for other modulation schemes, but this one's like fairly easy to compute, so do give this integral here a try yourself. Now, in order to compare the performance of different modulation schemes, it's typical to actually report the so-called bit error rate instead, where the idea is that you simply take the number of bits per symbol, which for the case of 4-quam would be 2, and multiply it onto the signal or symbol error rate. And the general idea is that if you have 4-quam, you don't have sort of one mistake causing 2 bits of error, but if you have 16-quam with 4 bits per symbol, then a single mistake causes 4 bits of error. So you have to include the number of bits per symbol as well to really get a sort of an accurate comparison of which scheme is performing better in a given situation. But anyway, let's take a look at how this signal, or rather simple error rate function even looks. So if we plot this as a function of the signal-to-noise ratio, we find that actually for a signal-to-noise ratio of 0, we get a simple error rate of 0.75 or 75%, which of course should make sense, because if all those 4 clusters are all centered at the middle, then of course there's going to be a quarter chance of landing in the correct quadrant. But we also see that if we increase the signal-to-noise ratio even to moderately good amounts, it actually drops off quite quickly. You can see we have a signal-to-noise ratio of around 10, and that gives us a error rate of around 1%. But if we boost it up to around 100, then it's already down to 10 to the negative 11. There's a pretty steep drop-off right here, where the risk of making a simple mistake decreases quite rapidly with improving OSNR. So that's kind of the reason why we want to have a high signal-to-noise ratio when we're doing optical telecommunications, because obviously the fewer mistakes we make in the transmission, the less we have to rely on like Hamming codes and other error correction procedures in order to get the correct data coming out. So just to make this a bit more sort of interactive, I've created this little animation we can play around with. So the basic idea is that we can increase the amplitude here, and then that should increase both the amplitude inside of this IQ diagram, as it's called, as well as show us the corresponding spectrum and the corresponding pulse here. So if we make a really, really clean situation like this, where you can see we have an extremely high signal-to-noise ratio value, then we get a perfectly sort of only signal-based spectrum. And we can't even see these little circles that represent the Gaussian probability distributions that we click on. And we get a very nice sort of clean pulse coming out. But then, of course, as we increase the signal-to-noise ratio, decrease it by increasing the noise, so now it's around a factor of 100 right here. Oh, it's a bit too far. Let's put it right here. So now you can see that at a factor of around 100, then we get a simple error rate of around 1 part in a billion. So we make like one mistake every time we send a billion symbols. And that corresponds to a spectrum that looks a bit like this, and a pulse that looks similar to this. You can see that the pulse, it's still pretty clean. You can easily see that, there's clearly a pulse going on here, but also has a bit of sort of fuzziness that could be the reason why we might make a mistake once in a while. But then if we increase the noise a bit further, see what happens now. We're around an OSNR value of 10, and you can see we have around 1 part in 100 chance of making a mistake, and that's when the IQ diagram looks a bit like this. Now again, I'm representing these Gaussian probability distributions simply with sort of flat circles, but again, you have to imagine that sort of a smooth probability distribution that extends over all of space here. So let's actually go a bit crazy and then decrease the signal-to-noise ratio even more. So now we're down to something that's very close to a SNR value of 1. It might be around here. So you can see that now we only really barely have the signal poking up over the noise here in the spectral domain. And we have this very, very noisy, very fuzzy signal coming out here. And you can see the signal-to-noise ratio is close to 1. And the simple error rate is like very, very, very bad. And let's just tune it up all the way and see that, of course, in the limit where... Oh, I was complaining because it has like a negative infinity value of the OSNR value in decibels. But the point is that you can see that if we increase the noise way too much compared to the signal, then all of these 4 constellation points sort of merge into the center. And that's why we see we have a simple error rate of 3/4, because of course if we actually have a simple incentive for the first quadrant, then you can see that it has sort of an equal chance of landing in each one of these. So we don't have a 25% chance of getting correct, and therefore 75% chance of getting it wrong. So that was a quick explanation of the connection between signal to noise ratio, simple error rate, and bit error rate. Obviously, the exact connection here changes a bit based on the modulation scheme, but hopefully this gives you a nice, clear introduction to how this sort of thing works. So thank you for watching, and stay tuned for more videos. Bye bye.